Okay. Okay, I think it's time for the last part of the afternoon session. It's my pleasure to introduce Weiqiang Wang. He's going to give the first talk of this session.
All right, so I will try to say something about what I have been interested in the last 10 years or so. And of course, this subject getting a little big, and the title, let me write down. A Drinfeld presentation of affine I quantum group. I will very much explain those words of what a quantum group, what I quantum group, what's affine, and finally come to the Drinfeld presentation. Well, let's even go back one step. If you start with semi-simple algebra, that's something we all use very often. And there are a couple different ways we can generalize it. One way is due to Drinfeld and Jimbo, you can just quantize by adding a parameter Q to it, and this is known as a quantum group. And on the other hand, you can, instead of the semi-simple E group and so on, you can oversee, you can study over real group and so on. This alternative way you want to think is in terms of so-called symmetric pair. And since I'm talking about the algebra version, I can also do the algebra version. So it's a symmetric pair. And if you have the algebra do the complex version, G and theta is an involution of the algebra. And you can classify this. This was classified by Kaplan, and it's very much the same classification as the real form on simple algebra. And in the last few years, this new picture emerged here. Let's call this quantum symmetry pair. This was defined around 2000 by Gail Lester, and it consists of quantum group U. And the subalgebra, I will denote by UI, and this UI is what I'm going to call the I quantum group. And you remember, quantum group is a top of algebra. It has a co-multiplication. This UI is not, it's a subalgebra of U, but it's a very special subalgebra known as coideal subalgebra. Under co-multiplication, you send UI to UI cancel U, not just U cancel U. Okay. And the first thing I want to try to explain is give you some example classical picture. I want to try to say this I quantum group contains the usual quantum group as a special case. Just like when you study a real group, complex group can be viewed as real, even as a single and so on. That's almost the same type of observation. So let me give you an example. I'm today only talk about some very special class of I quantum group, also some very special topic as in the title about the I quantum group. The subject getting very large. All those various construction of quantum group can be generalized for I quantum group setting. Let's consider the following involutions. Called omega is called the Chevalier involution or Kaplan involution. And if you have used the standard notation, EI, I not over the set simple root, and omega can send like EI to FI, FI to EI, HI to minus HI. This is the algebra involution, and this is one of my example theta, is my main example theta. Okay, that's the involution. Then you can talk about fixed point subalgebra. This a little variation I could add a scalar here, sigma I. Then I need a little sigma I inverse here to make this involution. This you can scale, that's well known. This non-zero scalar. It's convenient, turns out. And for example, if G is ACON, then ACON omega, this is can be identified with the skew symmetric matrix. So this is ACON. But this is not the kind of matrix form we like when we study Lie theory. But somehow in this I-quantum group picture, we are going to use this. So you sometimes do something you teach students, no, you should not do that. But after 20 years, you start doing that. All right, and this example, CG omega, I will call it split. This is only the type I'm going to consider split symmetric. Okay, it's a very, very special case. There are much more general class. But every complex simple Lie group has a split real form. This is the same word as split. All right, the second example. This example will tell you why quantum group are special case of I-quantum group. This is under the algebra setting. This is one very special case of symmetry. You can take a G, take a double. Then you can take a diagonal copy. This is an involution basically by swapping these two factors. That's the involution of the algebra. And so this G, literally, if you're interested in G, you see G thinking at this place. I'm interested in this thing and this quantization. All right. So the algebra G can be my target, my fixed point subalgebra under involution. So this picture can be quantized. Is what U tensor U and U. And how do you build this as a subalgebra? Well, a natural guess is you have co-multiplication. This is algebra homomorphism, then the image of this will probably do, except it's not quite. And turns out you need a little twisting by the Chevalier involution on one side. The Chevalier involution generalized to a quantum group in the most natural way. And you need this twisting so that the image is coideal. But no big deal. Let's take that for granted. So now the quantum group so for this reason, as I said, quantum group is special case for this I-quantum group. They arise from this quantum symmetry pair of diagonal. Okay. So the quantum group, my notation, if I use the Chevalier generate, I will call Ki if I then similar to the algebra, but if Ki becomes invertible, then you write a capital Ki. And this related notion known as Drinfeld double. I will denote by U tilde. And this is very similar, like it has the same to the EIFI, KI, but I replace KI inverse by KI prime. But KI prime very much satisfies those property KI inverse commutation relation of EI and FI. And as a matter of fact of that statement, KI prime in the Drinfeld double is central element. And you can do a central reduction, this go to 1, then you reproduce the quantum group U. So this quantum group is a central reduction of the Drinfeld double. And turns out it's convenient to have a version of this. Now let me define. This is still a Hopf algebra. Yeah. This algebra. Why one of the reasons I want to mention this is this arises from a Hopf algebra construction, and so it's natural. In the Hopf algebra construction, all these Chevalier generators they realize in terms of some modules over quiver and so on. KI inverse has no meaning, but KI prime has meaning. Modules are relative meaning. So this is a more natural thing. Anything you can construct categorically or geometrically, they are rising. So this split I-quantum group, UI, there are two versions. The first version I define as a subalgebra U, as I said. What is UI in this case is just generated by, in this case, extremely simple. In terms of generator BI, and this BI is defined to be Fi plus EI, PI inverse. I'm adding a little bit of scalar. So if you look at this, what the G omega is, the generator should be just Fi plus this scalar. Probably I should put inverse here and to make the notation more consistent, but no big deal. That is a scalar plus EI. Ki equal Q equal 1 limit go to 1 anyway. So turns out this is a good quantization definition. And this alternative version, which Lumi and I introduced, is on this Drinfeld double version level. You can also define subalgebra here. Sorry, this I doesn't mean index I. If that's your question?
Yeah, the BI goes.
This runs over all simple group. That's pretty bad. This I is I quantum group. This I is I tilde. My latex will look a little better.
That I is for internet.
That's up to your interpretation. Yes, has to start with as a joke, but anyway. Also, since by convention, I've been using I for the simple roots, so it's terrible. This my handwriting cannot distinguish these two very well. Anyway, this one is has generated I. This another Ki I will not explain right now. This Ki is central element, just very much look like in the Drinfeld double thing, like this product type of thing. Yeah, but this BI in this version, since I don't have inverse, actually is written EI Ki 1. Also, in the Drinfeld double version, this I quantum group has no hammer. That's the thing. This is I call the universal I quantum group. This is kind of the rest of this look like a flat family deformation. You just replace those scalars some hidden in terms of some central element. And turns out this is what the nature produces. It has several good advantages. So far, this construction, if you put aside the motivation, there's nothing wrong preventing you from saying, let's do cosmology. Okay, nothing you need to say G is semi-simple algebra. Okay, all this definition makes sense. Everything so far makes sense. But I'm not going to do object cosmology. I'm interested in the affine case. That's how we study in graduate school doing affine POA, right? Affine. So G hat is affine algebra. So it has cosmology presentation is 3I, except you add one more vertex. Here. But this class of the algebra distinguishes itself by having a second presentation as a loop algebra presentation. So this is also equal to the finite G tensor with the Laurent polynomial plus central extension. In my talk, the degree operator is irrelevant. Even you can go to the extreme, even the central extension is irrelevant, pretty much. This thing can be inserted. Okay. So my notation here, if you have element in G, a T power, let's write this as a N. Okay. So this G hat have generated in this form, you call the loop generator. So it's generated by, you can use the Sichuan generator in the finite part and the tensor with N. So EIN, FIN, HIN. There are plenty of generators here. They are infinite, but it shows you this loop algebra structure. And so it's useful. It has a lot of connections with POA. Now, let's redo this Chevalier evolution again, but now for G hat. I very much want to extend the finite part of Chevalier evolution for the affine part, put the affine part. But if you use the cosmetic definition, still the older definition still makes sense. Okay. Still EI interchange with if I and HI go to minus, right? So older definition, let me write down just one formula to remind you, HI, EI. But this I like include a 0 index. But turns out you can alternatively use the looper version. And these things, let me write this here as AN. Those two, A is in the finite part. And you have Sichuan evolution applied to this part. And turns out N goes to minus N. That's also is the corresponding Sichuan evolution on the loop part. So you will have corresponding G hat and the fixed point subalgebra. We are interested in quantizing this G hat omega. Well, this one quantization is as written. This definition makes sense as well. Okay, so we are interested in a new presentation. But before we are getting there, let me show you the classical picture, in particular in issue 2. So on the algebra level, it's very easy to write down the linear basis, even in the looper generator thing, or the generator. Okay, this G hat omega is generated by let me give you VIK. This is if I minus K plus some scalar times E sigma I and E I K. Together with something later, let me call it E I K. We minus H I K plus some scalar H I K. And this if I K notation means if I cancel with T to the K. So you can easily check claim if those are indeed actually invariant under the Sichuan evolution. I didn't explain what C is. C is a scalar construct out of this scalar sigma I or all I. Very much correspond to the imaginary. Okay. So these are the generators. And let me work out one particular case, ACU omega. Specifically, in this case, let me write down the relation. This case is not just generator, these are even bases. ACU2, this is not much room for the actual element. So I could drop I, just like use K there. This I is just a single one, EH. So in this case, the relation looks like something like this. The T is coming from the Cartan part. Beck is each other. Okay. And then you try to do a commutative T and B. Then what you get is 2 times B K plus N minus 2 times this little scalar C B K minus. So these are like a real root vector, like those F something, but F mixed with E. So this one H will make with F maybe is going up and lower. Because this T is involving the shifting up. Oh, must be one of them must be minus K. This one. So not surprising. And this is also relation between B and B. I will try to write down a more complicated relation than necessary. Because you could easily just compute a B and B relation directly in terms of H, but somehow I want to write it as a difference of the two, and this is given by minus K sigma 1 E0 minus K plus 1 plus C E0 minus K minus. That's all the relation I can write down about this fixed point subalgebra for ACU2. One comment here is this is why I bother even try to go to the generality, talk about with scalar. All the different scalar you put in the underlying the algebra, they're isomorphic. fixed point by the Schwarzschild involution in the case is n case, they are S multiple is ON for different choice parameter. But there are good reasons. Some of these reasons I'm not getting into. But for now, you could think that C instead is a scalar. This is a central element in this the algebra itself. That way of thinking help you to restore the grading. Otherwise, this the algebra look very poor for few people. So you don't like it. They do not preserve the degree. The nk go to n plus and this k minus. But if you think that this C has degree 2, actually the degree will be homogeneous again. And that is one of the several advantages of having these things around. But if you think it's scalar, of course, you cannot assign degree. You want to think this is central element. And you work with Drinfeld double level. These type of things can be covered. All right. Now, let's try to quantize. What we know before is due to Drinfeld. So, for the usual quantum group, a fine case, UQ is your 2 hat. This, of course, can be defined as Calabi-Yau, then as defined as Drinfeld-Jimbo quantum group. You just use the set presentation. But the claim is this admits loop presentation, and also known as Drinfeld new presentation. So this was written down by Drinfeld around 1986, many years ago. He didn't live proof, and Beck and then Damiani supplied proof sometime later. This was much highly non-trivial than the Q=1 case. For Calabi-Yau, this is a standard construction. You can give in one lecture, explain all the details there. Why the affine algebra has a loop algebra presentation. This one, well, Drinfeld didn't give a took more than a few years, more than another decade to correct it. So it's a start off, but this thing exists and is highly influential in math physics in developing its finite dimensional application. Turns out the quantum affine algebra has a very, very rich computing theory, finite dimensional. Okay. So our question now is become clear. We want to do the corresponding quantization. Because this UI here corresponds to this omega fixed point subalgebra G hat. We are hoping to ask the question, is this a loop representation? In the special case, Q=1 looks like something like this. That fixed point subalgebra in quantum affine is your tool. Is also a name from math physics known as quantum unsubbed algebra. Okay, but never mind. So let me remind you a little bit. Now we are specializing in this splitting affine quantum group. But let me now work on this Drinfeld double version. So this is U tilde and this is U tilde I. So my U tilde I has generated. The I is some other central element called this version of Ki is invertible, and I round over our affine simple roots. This is the Schwarzschild definition. This is given by Theo Lester and generalized to Calabi-Yau case to cope, but this split case was in the literature for a while. And you can write down a decent set presentation. In this case, was known earlier, but even for our Calabi-Yau case, the split type is easier. And that a few years ago, my collaborator and I wrote down in the Calabi-Yau case. It involves a new concept known as I divided power. That comes from canonical basis. Will take us too far away. But anyway, this is the algebra we are interested in. As Q=1 limit, this is the G hat omega. Okay. So we like to give a new presentation of this quantum algebra, UQ. let me write down one of the classical set relations try to remind you in this set type of representation how this look like. If Kaplan integer Cij equal to -1, I want to write down the relation between Bi and Bj. Bi, Bj, you should think that this is like a usual superposition generator Fi, Fj. Because by definition, Bi is equal Fi plus something. And Fi you should think as a leading integer. So when you try to construct find some relation between Bi, Bj, you look at the leading term, they are Fi, Fj. So they should have a cubic relation, usual set relation, Fi square, Fj, and so on. Try to use that as the first approximation. And to see, let's just try to do this. And quantum 2 of Bi, Bj, Bi plus Bj, Bi squared. If this is in the usual Drinfeld-Jimbo quantum group case, B is F, this is equal to 0. That's a Q set relation you are getting. If you specialize to the usual the algebra, this is a standard set relation. But in our case, even if you specialize Q1 using this generator and so on, this is not equal to 0. But this case was worked out by Lester, but I'm writing down the universal version of Lumian idea. So up to a scalar, still this scalar is non-zero. This Bi here, you cannot cancel it out. And this is already in the simplest non-trivial case. If this Cij is getting bigger, -2, -3, this formula getting worse and worse. Okay. So this set relation can get very bad. And if you are first time look at this type of algebra, look at this kind of relation, you will throw this algebra away. I don't think these are too interesting. Okay. Take a while to get used to it and to know these things will have some application. All right. So and now let me write down this C. I wrote down the classical case. This corresponds to basically the imaginary K delta. It should be as product over I K I. But this formula is not really not important. I probably don't need to write that. Because the imaginary rule can be written as simple rule in the classical case as some I. This is the multiplicative version of something like that. This is a central element. And the main point is in our SO2 example, you have those BIK generator, B low key in the classical case, and the PIK generator. BIK is more like the real root vector. HIK or TIK is more like imaginary root, because that's how they are composed. And in this Drinfeld construction, very much the generator is also very much similar. This can be generated by something like a IK, if IK, and something HIK. This last K is not 0. And I'm using the capital notation, just the corresponding lower P will be the usual loop algebra type of generator. Okay. The classical limit, you will go to the lower PEI cancel T to the K, that type of thing. And as I said, to construct this generator itself takes effort. Drinfeld never did that, but Beck, they used the Weinan group symmetry on the quantum group. It's like you want to shift these things in the loop direction K times. Those require some those translation. Okay, translation symmetry. And what you need here is the so-called Weinan group action. And Ludwig already defined the Weinan group action on quantum group any cosmology. So that was used there. So it's not surprising in our new situation, if you want to imitate, you like to do something similar. But one of the first problems here is the Ludwig Weinan group action acts on U tilde or U. These are automorphisms here. They do not preserve the subalgebra. Turns out this I-quantum group themselves is its own symmetry, its own weighted group symmetry. And nowadays I could refer to this as a relative weighted group symmetry. That terminology comes from the following. Any symmetric pair, there's a notion called the restricted Wang group or restricted root system or relative Wang root system. And associated to that root system, you have corresponding Wang group, relative Wang group, or relative weighted group, and so on. And turns out, remarkably, the whole package is generalized. Those corresponding relative weighted group, they are symmetries of this I-quantum group. For that particular purpose itself also is essential to work with the universal version without payment. And so, okay. So here you need the notion of relative weighted group action on the I-quantum group. This is not equal to velocity. And this indifferent generality has been recently constructed by Ming, myself, and Weinan Zhang, who's my student, sitting in the audience. Yeah. Yeah. Okay. There are different combinations of this also, there are different work here. Because the I-quantum group is extremely rich, okay? Even in finite type, you have A, B, C, D, E, F, G diagram. But the corresponding classification of the I-quantum group is in terms of stochastic diagram. There are 20-something diagrams. So I split cases only for each A, B, C, D, E, F, I give you exactly one. So it's a very special case. And anyway, we just admit such thing exists. Such things allow me to define the real root vector, quantum root vector, called the capital BIK. This is quantized in the example, those lower key b, BK or BIK. And this thing is obtained from the Chevalier type of generator DI. This is in the original cosmology type representation after DI. So generator apply some symmetry with a group symmetry to this. And this is translation in the direction I's fundamental weight direction K. And you in the usual picture for the usual algebra or quantum group, the weight is right. But
So let me understand it correct. So is it the break group action is sort of a quantum version of the vowel group,
yeah.
right? So if I set Q to 1,
yes,
this will go back to the vowel group. Is that correct?
In the logic case, yes. A logic case, the logic weighted group Q goes to 1. Those generated I will go to those familiar formula,
Right.
triple product exponential. And these are the corresponding classical relative weight of action. I could not find any formula in real group related. So I think our formula by special triple 1 is new. And also our formula used this notion I divided power. It's a special case of this I canonical basis quantum bond I introduced the last few years. And that's pretty.
Is it but is it still a Coxeter group? The limit?
It's a great group. You have a quotient group. Yes, you don't have a quadratic relation. You have the greater relation. Yeah, this is even finite type is not a finite group. So, because even in for the usually algebra, Wang group does not act on the algebra. Only certain cover or something. Yeah, you need the break group action. Yes. So the formula in the I world, I think even classically, as far as I know, did not exist. At least not the form we know. Our form is even they act on the integral form, and you can do the base change. I think it go beyond from the real group literature. Okay. So you construct the real root vector. After this, you construct the imaginary root vector. This imaginary root vector in the Drinfeld setting They are just obtained by the real root factor doing some Q commutator. And that's it. You find the right Q commutator. Like usually algebra is find the real root factor to a commutator. You produce the imaginary hyperbola. And turns out this is a Q version. In Q commutator for the usually quantum group you can do. In our case, also more complicated. They are lower 10. You need to correct. But it can be done. I will just write down the generator in the generating function form. I will not give you the precise formula. 1 plus qi minus qi inverse summation m between 1 is theta I m. These theta m are those imaginary root factors. This second form, we take exponential notation, qi minus qi inverse, and summation of m between equal 1 again, hi m c. Turns out in quantum case, you need a two-set generator. That was the case already in the Drinfeld presentation for those who know. I did not make this up. Turns out at peak one limit, this is not much different. But in a quantum world, everything is getting a little more important. Now let me write down our main theorem. This is in my paper with Lu-Ming in the case of ADE, split affine ADE, and then generalized by Weinan Zhang for BCFG. He also simplified the lots of proof. It's the proof sometimes it can be really difficult. The split affine I quantum group U tilde I admits the following Drinfeld type of representation. And you can take the generator. These sound those KI a little bit like affine, but in our split case, these are all central elements. And also C is this C also -1. Then our real root factor K, and you can write theta I, or use H notation. Either way. And different relation depends on which form you are writing. One is more convenient than the other. Okay. Let me write down some obvious things, something I all handle with Bacon mill. These are central elements. Turns out this imaginary root by Bacon mill. This is highly non-trivial property. That's if you get that property, you can check things right. That pretty much is our own experience. You see that I am for different I different M they commute. Okay. And now I switch to theta commute and H also commute. H and the theta just a different expression combination. HIN BJK is equal to M CIJ over N BJK plus N minus MCIJ M over N BJK minus N CN. This formula look a little bit familiar from the ACO2 case. This CIJ is Cartan integer. If you take J equal I, Cartan integer is 2. Basically, this is factor 2 in the classical limit. This is another factor 2. Okay. But in quantum world, look like this. If you kind of formally set our C to be 0, that look like a Drinfeld presentation. So our picture look like another further deformation of a Drinfeld presentation. Drinfeld half quantum group use only the F thing. These are kind of our leading of our formula. Okay. Let me write down 1, 2, 4. This one is your 2 case do not appear. But that's one reason I'm writing it's your 2 case some version of Q commutation among the real root vector Bij. They satisfy relation. Local like this is another Q commutator. Okay. And is equal zero. And this formula actually has a counterpart in Drinfeld-Jimbo's work. And let me write down one final formula in the presentation. I need to say this I not equal J case. So this formula you did not see it in the ACO2 case. But ACO2 case, you can still ask for this formula when I equal J. So left hand side is 3 for I equal J. In that case, you read the Cartan integer to be 2. And this is the formula left hand side. Turns out it's not equal 0 anymore. This rank one case is this is kind of E and F they interact. We produce each time in usual state. And this one produces something like Qi minus 2 theta I U minus K plus 1 minus Q minus 4 theta I U minus K C times the same to T. This is for the AO bigger than K case. And if A less than K, the right hand side needs to be changed. And this formula, in this specialized to the ACO2 case, I wrote down a formula. I wrote down a more complicated small b with 2 term difference. In that case, classically, you could even have a formula for a small b commutator, but that formula cannot be complex, as Drinfeld already showed us. Okay. This final formula I will now write down is a cell relation among these real root vector. And this one is involved, and it's explicit, but I'm not going to comment on this one. But and some of us, if you are working with vertex algebra, let me at least show you. You could rewrite most of the formula into a generating function. And they are pretty, I will say. For example, I will just give you one case. The theta I C W is like a W theta I C. And this is equal to 1 minus Q I C and J C W inverse 1 minus Q I C. Here's a minus sign here. Inverse times another term 1 minus Q I C I J C W C 1 minus Q I minus C. These are two rational functions. Yeah, again, in the quantum affine world, you will be familiar by setting C to be 0. The second term becomes 1. That's a formula you will see in the Drinfeld case. Okay, and this formula is essentially some theta function associated here. And the other formula can be equally written into the generating function in a very compact way. This formula and this formula. Let me just finish by making 1 or 2 remarks. This formula has certain further generalization from the split case to the what we call quasi-split case. And there should be further generalization, but this picture is complicated. It will take some time to sort out. There are many more fine cases. The problem with quantum group is there are many local cases, many local rank 1. They further many more local rank. Just like a real group, a real rank 1 subgroup or group, they are just not way beyond ACO2. Okay, we are lucky when we work with compact or complex B group, but this is just an ACO2 or sometimes work with PGO2 or some version. Yeah, but depending on the one. And the other thing is this Drinfeld presentation, they typically are showing up in geometric realization of a fine quantum group. And so we expect the same thing in the geometric realization of fine quantum group. This is the version you need. And they already used in the so-called I-Hao algebra realization of the I-quantum group of affine type, using the category of shape over the projective line or Weiqiang projection. And these are the version of presentation. Let me stop here. Thank you.